pretty happy about that study. So um, definitely we'll try and get to your questions. Like I said, we're going to try and break it up to into some bite-sized pieces here. So I'll get rolling. Um, so we're going to start off with just some basics intro to kind of soil fertility. The 4 R's are kind of how a framework to think about nutrient management. It's the way I teach nutrient management, to think whenever you make a fertilizer decision, you're making a decision or a plan based on the 4 R's. And this gets a little confusing for people because the 4 R's are all the same word, right? The right source at the right rate at the right time in the right place. So when we talk about fertilizer or even applying manure, any nutrient, we're talking about what's the source, how much do I apply, when do I apply it, or even how often if I'm split applying in the year, and where do I place it? And placement can kind of be three-dimensional. And am I injecting it? Am I tilling it in? Am I surface applying it? Um, am I band applying it on the surface or band applying it subsurface? So that can be placement. But I always caution people that sometimes we forget to think about when we look at this graphic that they made up of the right, the 4 R's. So source, rate, place, and time here in the center of the circle. Whoops, click there. Um, but there's these performance objectives around the outside that we have to consider that we often forget about. So first of all, it's the 4 R's, but in a well-managed cropping system, right? Because applying all the fertilizer in the world, if I haven't taken care of soil properties, if I don't have the right crop out there, and not doing everything else right, the fertilizer isn't the only thing in the equation. But also, we've got to think about that performance objective. And often, when we talk about nutrients and nutrient management, you've got productivity, right? How much tonnage am I producing? How much yield in that row crop? But at the end of the day, we're more interested in profitability most of the time. So that's a different performance objective. Or we could talk about quality, right? So maybe it's not yield. Maybe it's not necessarily how much money am I going to make off this crop, but what's the nutritional profile, particularly when I'm producing livestock. At the end of the day, it's different than a grain farmer. In a grain farmer, the equation is, dollars per acre in fertilizer versus dollars per acre in yield. Whereas when we're talking about pasture, hey, we're talking about dollars per acre in fertilizer to get a certain amount of product, animal product off of that feed. Um, Environmental, economic, these things are important as well. So the right nitrogen rate economically or to maximize yield might not be the right nitrogen rate to protect that stream or that water quality. So, the right can be subjective, and we've got to think about what is my objective, what's my performance objective here when we're talking about that. Now, also in the basics, now this evening mostly I'm going to talk about the macronutrients, the micronutrients, and liming. And I'm really going to focus on NP and K, the primary macronutrients. So the macronutrients are defined as what the plants take the most of up. And so that's NP and K are the primary macros, and the secondary macros are calcium, magnesium, and sulfur. Now, for example, a plant takes up way more calcium and magnesium than phosphorus. In fact, a plant takes up about the same amount of sulfur as it does phosphorus. As far as the macronutrients go, a plant needs, in this order, nitrogen, and then potassium, calcium, magnesium, and then phosphorus and sulfur last. But with the NP and K are the primary macronutrients because those are the ones we have to supply with fertilizer. The secondary macros, while the plant needs a lot of them, typically a soil in Kentucky will produce enough calcium, magnesium, and sulfur. We don't have to worry about fertilizing those if we're maintaining the pH in the right range for calcium and magnesium. Now with sulfur, that's starting to become a little bit of a special situation, and things like alfalfa, high tonnage crops. We're going to keep an eye on sulfur, and we'll touch on that in a little bit. The micronutrients, I'm not going to cover too much of those this evening. I'll mention them offhand, but again, a Kentucky soil will produce enough of the micronutrients. A lot of times, there's a lot of marketing that goes into selling micronutrients outside of maybe some boron in alfalfa. If I'm taking care of my soil pH, I shouldn't have to buy micronutrients. Our soils have the plants take up very small amounts of these nutrients. Certainly they're important, but our soil supplies them if we've managed the pH correctly. Now, there are some exceptions to that rule, like all rules. We can do things that mess up the micronutrients. If I overlime, if I underlime, some liming materials in some areas, they'll put out steel slag from steel smelters as a liming material, and that can really throw the micros out of whack. Not always. I've done a lot of work, and some of those steel slag products are really great, but they can, in certain situations, have some chemistry that will throw the micros out of whack. But in general, let's take care of the lime, and we won't have to worry about paying for micronutrients. Uh, Liebig's barrel is kind of a fundamental basic of soil fertility, and all it says is that it's Liebig's law of the minimum. And what's interesting is Justus von Liebig. So there was all these chemists in Germany in the mid 19th century that were really getting into soil fertility. The world populations were booming. We were going through the Industrial Revolution. And that's when we really discovered the need for phosphorus fertilizer. And Justus von Liebig got a lot of this credit. It's called Liebig's Law of the Minimum. But it was actually Carl Sprengel who developed that law of the minimum and Liebig's barrel and published it first, but Liebig got credit for it. But it says that the nutrient that's essential, that's available in the smallest quantity, is what's going to limit production. And what this means is it's like a barrel, these staves. And if one of these staves is low, like phosphorus, it doesn't matter how much nitrogen I add, phosphorus will limit my yield potential. It's basically a way of saying everything that's essential, I need to have right. And then the other thing I always want to remind folks about is that soil productivity is different than soil fertility. And so there's an old saying that says a productive soil is fertile, but a fertile soil is not always productive. So what's that mean? Well, I can add all the fertilizer in the world and my soil is fertile, but I may not be able to grow a crop because of compaction, right? And so that's a productive soil has enough moisture, has the fertility, it has the pest management, it has the right crop selection, good soil structure. All of these other things are there because sometimes we want to throw fertilizer. We think that that's the answer to all the problems, right? And I'm a fertilizer person, so I'm not complaining, but oftentimes I'll go out to look at a crop and it's clear phosphorus deficiency. And then I'll look at the soil test and there's plenty of soil phosphorus. Look at their nutrient management plan and they've applied plenty of phosphorus. Well, it turns out the pH is too low. So it's expressing phosphorus deficiency because the pH is too low. Or compaction. In corn crops, we get sidewall compaction from planting when it's too wet. And you'll have tons of sulfur deficiency or phosphorus deficiency in that field, but you actually don't need fertilizer. The problem is it was planted a couple of days too early and it, wet soil, and we got sidewall compaction, didn't get good early root growth. And so some of these deficiencies started to show up. When we talk about that soil structure, that sidewall compaction, this is the other thing, probably one of the most important things from a fertility standpoint. For example, someone have a question? No. Okay. One of the most important things from a fertility perspective is that compaction, because if we don't get good root exploration, inches of root matter. For example, phosphorus moves by diffusion to the root. And so that nutrient has to be within a 1/4 inch of a root for the plant to use it. So the more roots we have, the more phosphorus that plant can get up. And so if I've got compaction, doesn't matter how much fertilizer I put down, the plant just doesn't have enough inches of root out there to get the nutrients it needs. And a perfect soil, an ideal soil, is half something and half nothing. What's that mean? Well, the something is solid material, either organic matter or mineral soil. And the nothing is pore space. And you want that pore space to be half air and half water. And in fact, when you have a compacted soil will seem very wet, but it has less total volume of water, because what you're doing is, of course, the mineral soil isn't going anywhere. You're squeezing out that pore space and you end up with something that's 75% solid material, only 25% pore space. And then basically all your pore space is filled with water. And so when you feel that soil in your hand, it feels really wet. And you think, boy, this soil's got a lot of water in it. you don't necessarily have more water, you just have less air, so it feels more wet. And so compaction is probably the worst thing we can do to a soil. Sometimes we can't avoid it. We tend to have a lot of wet weather these last few years, and so we have trouble avoiding it. Let's talk about pH, because pH is really the most important thing when it comes to nutrient management. We call soil pH the master variable. And so if I'm growing a hay crop or have a pasture or any crop really, this is the first thing I look at on a soil test. Someone calls me with a problem, the very first number I look at is pH. Now, we don't want to get the pH too high. We want to get it in that kind of sweet range of about 6.5. And, it influences everything. And so this figure here on the left side of the screen, it shows the availability of nutrients for different ranges of pH. So, for example, phosphorus between 5.5 and about 6.8 is the most available, right? And so if I drop below 5.5, I'm going to see phosphorus deficiency no matter how much fertilizer I put out. Potassium, sulfur, similar. Calcium and magnesium, we want it to be up above 6 to take advantage of what's in the soil. And then really the reason, and liming was probably the first soil fertility activity that ancient people ever did. And the reason they saw a benefit was twofold. They were seeing a phosphorus response because when they limed, they were able to utilize the phosphorus already in their soil minerals, but also aluminum toxicity is a big problem. And so when we have an acid soil, the aluminum becomes soluble. And so that it becomes soluble, can be taken up by the plant, and really you'll see root pruning and just it'll smoke a crop. And so that's a big problem. And that's why we want to keep our soils limed up in the right range. Here's some data out of Eastern Kentucky that's sort of interesting. So these points, if you look at the horizontal axis, we've got soil pH, and I've got extractable phosphorus. Boy, I keep clicking by accident. Sorry, folks. We got extractable phosphorus on the vertical axis. We've got pH on the horizontal axis. And this field, when we went there, we were going to do some research on this field, and they said, well, the pH is good. We're averaging, around 6 on our pH. The soil phosphorus isn't too bad. It's in the medium range. And so this is parts per million. So multiply this by 2 to get pounds per acre of soil test phosphorus. So this would be, 15 would be 30. And so above 30, we're saying we don't need phosphorus. Well, they'd been sampling this field. It's a small field, and they'd been sampling as one field and getting one soil test result for the field. But look at how low this soil pH is. There were a lot of points. So we went in, we sampled this field. Every 10 foot, we took a soil sample. I mean, we took a lot of soil out of this field. We took about 3,000 soil samples out of this field. And so what we found was, as we got out into the middle and the far edge of the field, that pH dropped down. And up by the road, the pH was pretty high. And that road probably used to be a dirt road. And so you probably had limestone dust from that dirt road and limestone down there in the mountains blowing off and raising the pH up by the road. Well, when you raise the pH, you increase the availability of the phosphorus. And so when they sampled, it looks like they were sampling close to the road and not getting out across the field to find out that the rest of the field, as a matter of fact, most of the field had a real problem with low pH that was decreasing the phosphorus availability. And that's because of what we see over here on the right, that when we have that low pH, like we see here, 4.5, 5, the iron and aluminum, which we have a lot of in our soils, is going to precipitate out that phosphorus so the plant can't get after it. Now, out west where they have high pH soils, they have a different problem because calcium takes out the phosphorus. And if you overlime your field, you'll have that problem. Calcium will suck out the phosphorus and the crops can't get after it. But in that sweet spot, 5.5 to 6.8, that's where we see the best availability. And so what is soil pH? Well, it measures the active acidity. So that's not the only thing we need to know, right? It doesn't tell me how much lime I need. Some folks get these at-home test kits to get their soil pH. They're worthless for managing lime because they don't tell you anything about lime requirement. You've got to send it to a soil test lab. Here at the University of Kentucky, we use the Socorro buffer to get the lime requirement, named after actually our lab director developed that test, and it's used throughout the Southeast United States, the Socorro buffer. And that tells us how much lime we need. So we have to have those two numbers. We got to have soil pH, which is the active acidity, and we got to have the lime requirement. You can think about it like an iceberg. We know that most of an iceberg is down below the water level, right? And what we see is just that tip of the iceberg. Well, soil pH measures the tip of the iceberg, and the buffer pH measures the base of the iceberg, because you basically hit that soil in the lab with an acid solution. You see how much it drops, and you want to see how much it drops, to see how much of reserve acidity is in the soil, so that you can put enough lime out to handle that reserve acidity. And so this is where we talk about light texture soils, heavy texture soils being better buffered. The more clay you have, the better buffering they are. And so when you hear someone say, well, that soil is really well buffered, that's a heavier soil. You have to, if we look at the soil pH and the lime rate and what it does to the soil pH, a heavy soil, I can add a bunch of lime and not get very much change in soil pH. In a light soil, sandier soil, I can add a little bit of lime and get a big change in pH, right? And this works in reverse. So while I need more lime to see my soil pH change on a heavy soil, it will take longer for it to drop back down. Whereas sandy soil, see, I grew up basically on beach sands in Delaware. And our soils, we have to lime almost every year, because a little bit of lime will bump it up, but they drop right back down in a year because they're light textured and they're poorly buffered. So what is lime? Lime materials are typically oxides. So that's that O2 that we're looking at there. Hydroxides, that's that OH. I'm going to teach, there's going to be a little bit of chemistry tonight, but not too much. You got your carbonates, that CO3, silicates, SiO4, of calcium or magnesium. So this is going to be a real important part. We're going to hammer on this for a minute. That oxide, hydroxide, carbonate, or silicate is what we call the anion. See, they're all negatively charged. This has -1, -1, -2, -4. All right, that's an anion. It's negatively charged. And that's what's doing the work to lime up your soil. Calcium or magnesium do not lime soil. So some people think, well, I can apply gypsum. That's calcium sulfate, and it's going to lime up the soil. Nope. Doesn't work, because the sulfate doesn't take a hydrogen out of solution, and calcium doesn't help us. Calcium and magnesium are not lime. Lime, what does the work is that negatively charged anion, that O2, OH, CO3, or SiO4. So we have things like regular old ag lime, that calcitic lime, dolomitic lime, which has some calcium and magnesium. So if I need some magnesium, this is a good way to get it. And also dolomitic lime usually goes a little bit further because of the weight of magnesium. And that's something we'll talk about in a minute. Quicklime, typically too expensive for ag uses, but if you got a new piece of ground and you want to change the pH really fast, something like quicklime or hydrated lime is going to make a really rapid change, but it's going to be more expensive. But the calcium and magnesium don't lime the soil. It's that hydroxide, oxide, carbonate, or silicate that removes the hydrogen ion from solution. So let's talk about that for a second. So here is the lime equation. This is chemically how we write it out. So we've got this anion of calcium or magnesium typically, and they have to reduce the amount of hydrogen, and therefore this is a little bit of fancy chemistry. We won't get into that, but basically we're trying to draw down this hydrogen, because when I measure pH tells me how much hydrogen I have in the soil. The lower the pH number, the higher the amount of hydrogen in the soil. And so when I add this ag lime, this calcium carbonate, it dissolves in the soil water, and I get a bicarbonate hydroxide, and the calcium just goes off on the soil CEC. It's not doing any work from here on out. That hydroxide is going to pick up that hydrogen and form a water molecule. All right. So we can actually, if you throw a lot of lime, too much lime on the soil, or quick lime or something like that, you can actually, there's two things that happens. You drive off carbon dioxide, which I didn't show in this equation, and you produce water. You can actually wet up a soil by over liming. That's, would be hard to do, but it can happen. We've done it in the lab. But look at this, that hydroxide that's coming from the carbonate mixing with the water. So the calcium's not doing anything. It's just going off and sticking to the soil CEC. And so we get this hydroxyl that forms and takes that hydrogen out to form H2O or water. So how do we quantify quality of lime? Because there's bad limes, there's good limes. At the end of the day, I don't mind using a bad lime if dollars per acre it costs less. So your soil test recommendation comes back with a pure lime recommendation. If your lime is 100% CCE, calcium carbonate equivalent, and your RNV, which takes into this account the fineness factor, is 100%, then that's what the soil test tells me. The soil test says 2 tons per acre, pure lime. Well, my lime might be 50% RNV. And so that means it's only half of that purity. And so that means I'm going to use twice as much. So if my soil test says I need 2 tons of pure lime, my quarry has 50%, then I'm going to put out 4 tons of that 50% to get the job done. And the way we get at that is by looking, man, I keep hitting the button. Sorry about that. The way we get at that is by looking at the chemistry. So the calcium carbonate equivalency. So we just compare that to a pure calcium carbonate. Liming material, like I said, that dolomitic lime with the magnesium can exceed 100% because the CCE on a weight basis, that magnesium carbonate can neutralize more acidity than calcium carbonate because magnesium is lighter. And remember, the carbonate does the work. It weighs the same in each of these. So we look at magnesium carbonate, calcium carbonate. This molecule weighs less than this molecule. So a ton of this goes further than a ton of this. The size of limestone particles also determines how quickly and completely the limestone dissolves. So really coarse stuff isn't going to break down this year or next year. And so we do fineness factor. And every state has a little bit different way of doing this. So if you get your lime out of Ohio or something like that, it might be a little bit different. Not a big deal. But we look at it and say if it passes a 10 mesh sieve, which is a 2 millimeter hole, pretty small, but not a 50 mesh sieve, then it's 50% effective. So it's less than 2 millimeters, but it's bigger than that 50 mesh, which is 0.3 millimeters. Then I'm going to get half of that out of it this year. The other half I'll get in future years, next 3 to 4 years. If it passes a 50 mesh sieve, then that's going to dissolve this year. So if it's smaller than 0.3 millimeters. Particles that are bigger than 2 millimeters, we give 0 credit to because they won't dissolve in the next 3 to 4 years. So we don't count those. And so we add that up and we come up with this RNV, and that's just relative neutralizing value. And so when you're picking a lime, you look at that RNV, and maybe you have some options from the different quarries around you, and maybe you need more of the cheap lime. And so that runs up your trucking costs. So maybe the little bit more expensive lime is actually cheaper because your trucking cost is less. You know, you got to pencil it out, and we have calculators online that help to do that. And I'll show that here in a second. Time before planting it, again, if you've got a new piece of ground, one of the common questions I get is renovating strip mines, and they want to bring that pH up really quick. Then maybe you pick a quicker acting line with more finer material. High value crops like high tunnels, tomatoes, things like that, folks are going to go with a more expensive lime. But typically with pasture, the cheaper, easily available lime is probably what we're going to look at. And if your soil test magnesium is low, go with that dolomitic lime. If your soil test calcium is low, or you have like really high magnesium, you might want to go with a calcitic lime. Now, some folks really fuss about hauling magnesium to their calcium soils and calcium to their magnesium soils because they think magnesium makes a soil wetter. And there's some of these so-called experts on YouTube that I blame for this, that say high mag soils, magnesium makes soils wetter, so you got to haul in calcium to dry out your soils. It's not true. Sometimes just because there's correlation doesn't mean it's cause, right? So what happens is the parent material that contributes magnesium to the soil is prominent in places that are wet natured soils. It has nothing to do with magnesium, but you go out, you pull a soil sample, high magnesium, that's a wet spot in the field. Oh, it must be because of the magnesium. It's not the magnesium. So hauling calcium in there isn't going to dry that soil down. But there's some folks on YouTube that preach this, and I know a lot of people kind of follow that, but I wouldn't spend extra money on that for sure. Lime can be applied anytime between harvests of crops with pasture, pretty much anytime. Again, with the steel slags, if you got animals out, I'd be cautious. I have a friend that runs a soil testing lab up in Pennsylvania, and they had a story where they were using steel slag to lime, and they had some high dollar sheep out there, and they lost most of the herd because that steel slag had come out of a stainless steel factory and had really high molybdenum. And so they lost a lot of lambs of a very high dollar sheep herd. And so you've got to be cautious with that with animals out. Lime moves slowly through the soil profile, tilled soil. So if you're going to till because you're renovating a hay field or something like that, it's a good time to get your lime out. But in no-till, you're going to have pH stratification. So the best thing to do is to kind of stay up on your lime plan, soil sample regularly and lime regularly. Have a plan and just stick with it where every year or 2 years or 3 years you're liming. And so that you're adding a little bit at a time, because if you have to add a big shot of lime all at once, it's going to take a long time to move down to the roots. And so if you're adding a little bit every year, it's just going to constantly kind of leak down through the root profile. Rule of thumb is that lime works its way down about 1 inch per year. So, if you're applying a little bit of your lime every year, it's just going to be constantly a wave of that lime moving down through the soils, which is a good thing. The most precise lime recommendations are only accurate as a spreader. A lot of times you're hiring someone to come in and spread, but it's worth checking and talk to your custom applicator to see, because lime equipment, and I've spread a lot of lime, it changes every year. A lot of people just, they say, well, I set the gate, this is the speed. But lime in particular, it wears those mechanisms. And so, every year you've got to recalibrate. Soils can be over limed. We don't talk about that enough, in my opinion. I've seen that frequently in Kentucky. I've seen lime recommendations for soils where the pH was over 7. If your soil pH on your soil test is over 7, you should not be applying lime. Over liming is a problem, and it's costly if you want to bring that pH back down. So, soil testing is our friend. If your soil is what I would consider moderately acid, pH of 5.2 to 5.7, a single application of either before or after tillage is fine. If you're tilling, if not, a single application once per year. Strongly acid soils, so less than 5, you're going to have a high lime recommendation. You're going to want to split that and apply twice per year. And this slide says tillage, but clearly in a pasture, you're not going to have a lot of tillage. So I'd be splitting that. If my pH is below 5, I'd take that lime recommendation and split it up. And every 6 months, I'd be liming until I got it where I need it. Lime should be the first dollar you invest, because your other dollars aren't doing any work for nitrogen, phosphorus, and potassium if your soil pH isn't where it needs to be. So when I look at a field that needs to be renovated, I'm going to put most of my money in the lime pile, a little bit in the nitrogen pile, a little bit in the potassium and phosphorus pile. But the lime is what I want to get right first if I'm renovating a field. And, maybe it's too costly to renovate all your fields at once. And so you've got to kind of have a plan, a long range plan, and say, I'm going to work through my fields and get the pH where it needs to be over time. So that lime requirement, pure lime requirement, now I'm talking about is 3 to 4 tons per acre. You're going to split it up. So before I talk about lime materials, let me pause for a second and see if anyone has any questions. I'm going to open up the chat box here. All right. Does anybody have any questions?
If you do have any questions, feel free to put them in the chat box. I don't see anything coming in right at the moment, Doc.
All right. Nothing floating in here. So I'm going to hide this and go right into this next section here about lime and materials. And maybe this will spur a little bit of conversation. So when we talk about lime materials, I told you that we had calculators available online to look at comparing different quarries. And so there's the URL for the website. And if you don't get this down real quick, I'm going to give a PDF of my slides to Philip here so he can share those with everybody. So there's the website. You go to that website, and we're working on getting a map up so that you can look at your location on Google Maps and see every quarry and what their most recent quality test was. We're getting that put into Google Maps. But you can poke in here the quarry, the RNV that you're told that they have, what the price is, the hauling, the spreading, what your soil test rate was for 100% effective lime, and your field size, and then it will output what the cost per acre is for each one of these with those factors so that you can compare across the quarries closest to you. I often get questions about pellet lime. It's a lot more expensive than regular old ag lime, and some folks say, hey, is this worth the money? Less than scrupulous salesmen will say, look, I know your soil test says you need 2 tons per acre of pure lime, but you can get by with 500 pounds per acre of Pell. That's not true. Let's go back to that lime equation. It comes down to how many tons of carbonate am I applying? And Pell isn't magic. It's regular ag lime. And so it's calcium carbonate compressed into a pellet, glued together with what we call lignosulfate. It's a high quality lime, so it's going to have a high CEC. As a powder, typically it's a very high cost, high quality lime that they've compressed into those pellets. But at the end of the day, you're still going to have the tonnage that matches whatever the RNV is of that material. And it's probably, if your soil test called for 2 tons per acre of pure lime, most Pells are labeled as 100% RNV. You're going to need 2 tons per acre. You can't get by with a 1/4 ton. Also, folks say, is it faster? It is purer than ag lime. It might take less Pell lime than an ag lime that's an RNV of 70% or something like that. But that glue that's holding it together has to melt. And so, it's also, so that's going to take a little bit longer. But my bigger concern is that with ag lime, you have some fines and some courses and you get a little better coverage. Lime doesn't move a great distance in the soil. And so, you don't get as complete coverage with a lower rate. If your pH is in generally good shape, I'm not as worried about that. But if you got a big pH problem, it can be an issue. So if I'm going to invest in Pell, there's nothing wrong with it. There's drawbacks, but what are the positives? It's really easy to handle. If I have a small area, I can spread it with a spinner that I probably have on the farm. I don't have to bring in a lime spinner. I can get it on pallets, so I can handle it myself. If I've got a low lime requirement in a small field, I may be willing to pay the extra money for that Pell just because it's so much easier for me to handle. So that's, a definite advantage, but don't believe that you can use, way less than it, or, that it's magic in some way. You still need X pounds, so many pounds of carbonate per acre based on your soil test. And that equation doesn't change. Liquid lime, kind of the same thing. It's a high quality lime product dissolved in water. It has its uses and it has its drawbacks. It's typically a high quality lime, very small particle size, so that it will dissolve in the water. It's going to act quickly, but it's going to be one and done. You're putting it in already dissolved, so it doesn't have to dissolve. So it'll get down the soil profile a little bit. But next year, it's not going to have any reserve. That ag lime, you got those coarse particles that break down next year and the year after and the year after. So this is a small land area, high value crop, and I need a quick turnaround to bump that pH this year. I'm going to use liquid lime. But per ton of liquid lime applied, you would only be getting a 1/2 ton of lime because it's about half water, right? And so again, I've seen folks sell this and they go, hey, look, you can put down 500 pounds per acre of this stuff. And it's the same as 8,000 pounds per acre of regular lime. It's not true. If you're putting 500 pounds of liquid lime down, you're only putting down 250 pounds of lime. So if you need 2 tons per acre of 100% effective lime, you would need to apply over 4 tons per acre of liquid lime. So that's over 700 gallons per acre. Now, I've had people tell me, look, I use liquid lime because I have a sprayer and I have steep hill slopes. And I like to use the sprayer and put liquid lime down. Okay, that's fine. If your soil test calls for 2 tons per acre, then figure out how many gallons per acre you can put down with your sprayer, and you're going to have to make 8 trips to get the amount out there you need to do the pH work that you need. So just kind of a cautionary tip there. Now, this is my favorite part of the lime talk. This keeps coming up. We wrote a newsletter article about this a few years back, and it just I get a couple of calls a month for the last 4 or 5 years about this product, calcium chloride. AgriCal, AgCal Pro, ProCal, AgriGold. They keep changing the name and changing their website, and they got some fancy marketers, right? But it's calcium chloride, all right? Now, in peanuts or apples, they'll apply calcium chloride for the calcium because it's a really soluble version of calcium. And in apples, they'll foliar apply it. In peanuts, they'll apply it on really sandy acid soils in Georgia. There's specific uses for it. But on their website, and they keep changing their name and changing their website, but it said originally, liquid calcium presents growers with an alternative solution to lime applications. Calcium neutralizes soil acidity. Ag lime tends to be insoluble, could take years to break down and show its effectiveness. So this all is quotes directly off their website. And I've seen this stuff sold on Craigslist here in Kentucky. So what about so we wrote this newsletter, and this is what they posted on our website. I hope Josh McGrath will need good lawyers. It turns out I didn't need any lawyers. It turns out if you tell the truth, you don't need lawyers. So anyways, I thought this was funny to kind of show some of the comments that they posted on the articles that we wrote about their products. But here's the marketing claims. Liquid calcium presents growers with an alternative solution to lime applications. Calcium neutralizes soil acidity. Well, we just went through the lime equation. And so you all know it's the oxide, the hydroxide, the carbonate, or the silicate. Calcium has nothing to do with doing the work. And so calcium carbonate plus water makes that hydroxyl that takes the hydrogen out. Now, if I put calcium chloride here instead of calcium carbonate, what would happen? Now, it doesn't happen because there's not enough energy. You need a big energy source for this to happen. But if I put calcium carbonate in here and dissolved it, and if that chloride picked up that hydrogen, because chloride is negatively charged, that Cl is negatively charged. So if that chloride was here, HCl is hydrochloric acid, right? It's an extremely strong acid. That doesn't happen because the way we make hydrochloric acid is by hitting it with a lot of energy. So it's a little bit different reaction than the lime reaction. So if it did do what they said, if that did take the hydrogen out of the soil solution, it would actually be forming a very strong acid. So that doesn't happen. So we know that's not true. Ag lime tends to be insoluble and take years to break down and show its effectiveness. So they said this, and there's a partial truth here. Limestone can be moderately soluble, but the finer particles in limestone are soluble and provide available calcium pretty quickly. So, even the worst ag lime has a couple 100 pounds per ton of fine particles in it, right? Just from the rock busting up. So their calcium chloride product, according to their website, is 10% calcium. So if you didn't need calcium, they recommend a rate of 2 to 5 gallons per acre. It weighs about 11.07 pounds per gallon. So that's 2.2 to 5.5 pounds of calcium per acre that you're applying with their product at their recommended rate. So they're saying that the ag lime doesn't provide the calcium quick enough to the crop. There are 800 pounds of calcium in a ton of calcitic lime, assuming it's 100% effective calcium carbonate. So even a very low-grade agricultural lime, let's say 50%, will typically provide a couple 100 pounds of soluble lime. So if I had a 50% RNV lime, I'd still have 400 pounds of calcium in that first year that's available. So even a not very good ag lime is going to put down 400 pounds versus 2 to 5 pounds of calcium. So this stuff is completely bogus. If someone's trying to sell you this, don't buy. It's not worth the money. So that's the whole pH section. And next we're going to talk about soil sampling I see there's a question about spacing and pattern for soil sampling. We're going to get into that because the whole next section is going to be about soil testing. Is there any other questions? I'm going to take a breather here and see if there's any questions.
Just a reminder, if you do have questions, make sure you can put them in the chat. You don't have to wait till the break to put them in there. We'll get to them just as soon as we can.
Philip, have you guys seen any of that ProCal or AgriCal in your neighborhood?
I've had questions about it. I do not know anybody that has applied it, but I have had a few questions come in.
I guess they got really kind of sideways with me because they actually made it so I couldn't look at their website from the University of Kentucky servers after we wrote that article. They had blocked me from their website. So
I heard something about that.
And I got a buddy out in Oklahoma that's doing some pot trials with it to confirm what we already know. But I didn't think it was worth even running it through the lab because it's just basic chemistry. So, all right. Well, and again, let me know if you got questions. We're going to just kind of keep plodding along. So we're going to get into soil testing. And you know, that's the basis for lime management, but also now we're going to get into that phosphorus and potassium. Because that's, you know, soil testing is how we handle potassium and phosphorus. So soil testing is really 4 separate activities. So when I say soil testing, I'm talking about collecting the sample, sending it off to a lab for analysis, getting results back, and then those recommendations. And traditionally, collecting the sample is viewed as the limiting function. Like we're pretty good at in the lab at soil analysis. Interpretation of results, there's some philosophy, so you can get different recommendations from different sources. To just take a different approach, and different people have different approach to fertilizer management. But getting that field represented in your soil sample is going to be really the basis for the best recommendation you can have. So I said, you know, I do a lot of my research is in precision ag. And so I do stuff like grid sampling, and I do things like you know, zone management, and we could talk about that. If you have questions about that, we could talk about it. I find that there's not as much precision ag in kind of the hay and pasture world. So I don't cover it in this presentation, but we can talk about it. But you want to collect a representative sample. So remember back to that slide I showed where they just sampled along the road and it gave a false sense of security. So you want to make sure you get out across that field and stick that soil probe in the ground a bunch of times. You want to, you know, UK recommendations say 12 or more soil cores per sample. So you stick the probe in the ground 12 times, put it in the bucket, thoroughly mix it, crumble it up and thoroughly mix it. Now remember, they're gonna, when they analyze that soil in the lab, you send in that bag of soil, they're using only about a tablespoon of that soil for the analysis. So you've got a tablespoon of soil that's representing 10 or 20 acres. There's 2 million pounds of soil per acre furrow slice. So you're using a tablespoon, and let's say you got 10 acres in that soil sample. So you've got 20 million pounds of soil, and you're using a tablespoon to recommend it. So the best thing to do, and people go, well, then, well, is it really worth it? Yeah, it's worth it because our soil test recommendations are pretty good. But get across there. We say 12 samples, 12 subsamples, 12 cores per sample. The research actually indicates you should have 20 or 25 cores is where we start to converge on the right number. I think the reason why they wrote up the extension fact sheet to say only 12 is because they didn't want people fussing at them that no one's going to take 20 cores. But you know, it's worth doing it right if you're going to do it because you've got a big investment in fertility. I always say that a soil sample for $7 or $9 or whatever it costs to have your sample analyzed, in a lot of counties it's paid for up to a point. That's the best $9 you'll spend on your farm. When you think about how many hundreds of dollars you spend on fertilizer, for $9 you get a pretty solid recommendation. So you might as well do it right and make that $9, you know, pay off. So go out there, stick that probe in the ground 20 times. You know, zigzag randomly. You want to miss the cow patties and things like that. really randomly run around there and get a bunch of samples. Determine what area is to be represented. Again, 10 acres, 20 acres. You might not want to go bigger than that unless the field's really uniform. Know if you've got multiple fields combined into a bigger field. For example, if you've got a small tobacco patch that's not tobacco anymore out in that field. Or what if there used to be an old farmstead there with a barn and some livestock? There's going to be a spot close to that barn with higher fertility. That tobacco patch is going to have higher fertility than the rest of that pasture. So separate those out. So if there's a man-made area in the field that's going to be different, and if you have knowledge of that field and it's there, take a separate sample for it, just to kind of, don't let it, or just leave it out. If it's a really small area, don't include it in your sample that represents the rest of the field, because again, think back to that slide I showed where they sampled close to the road. It made the sample come back higher and say they didn't need fertilizer when they did. So if you have that old tobacco patch and it's 1 acre inside a 20-acre pasture, it'll push your number up, cut back your fertilizer rate. And yeah, that's right for that little 1 acre, but the other 20 acres is suffering because it got brought down by that area. So you can just exclude it if you're not going to treat it separately. As far as natural features, topography, slope, and elevation tend to track with nutrient need. So side slopes, tops, knolls, and bottoms tend to be very different. So if you wanted to do a little eyeball precision ag without getting too fancy, you can have a topographic map that you download off the internet or web soil survey. Go onto the web soil survey of NRCS. If you Google that, you can actually find your farm, draw a box around your field, and it'll tell you everything about all the soils on that field and slopes and all of that stuff. And you can sample them differently. So if we look down at this, maybe this toe slope, and then up here on the side slope, and then up at the top, maybe I'm sampling it different, or maybe I'm just doing something very simple. Soil texture, color, slope, drainage, past management. This can all kind of be things we keep separate. Now, if I'm soil sampling to diagnose a problem, I'm going to sample the troubled spot, get one sample for that, and I'm going to go into the good area of the field and get a separate sample and compare the two tests to find out what my problem is. But most importantly is a map and good records. Oftentimes, folks come to me with a soil test report for this year, and I will ask them for the last soil test report for that field, because good records is actually the best thing that you can do for management of a field, because every soil is different. Our recommendations are meant for an average field. And so if you have your soil test reports for that field going back, maybe you've got 20 years of soil test reports in your folder. Well, you can plot those out by year and you can see, hey, my phosphorus has been steady going down. Or maybe what's happening, and we see this all the time in the pasture, if you use anything like 19, your phosphorus will climb and your potassium will go into the basement. And this is a huge problem in hay and pasture production. Anything like 19, 10, that's bad for hay, because hay takes off way more potassium and phosphorus, way more. And if you're putting out 19, you're putting down the same amount of phosphorus and potassium. So you're building phosphorus, which is expensive, and drawing down potassium, which really hurts the yields. 9 times out of 10, when I go look at a hay crop, it's potassium limited. We're losing money by not having enough potassium out there. So, keep a good record, track that over time. How to sample. Our recommendations are 4 inches in a pasture or no-tilled area, 6 to 8 inches in a tilled area. You look at that soil probe, a little trick. We take those rubber biscuits that you put on your air hose to keep it from retracting up into the shop ceiling. They clamp onto the air hose. We take those and we clamp them on our soil probes so that we can sample fast and get the same depth every time. So we put a little Sharpie marker above that biscuit so we know if the biscuit's slipping up on us. And so we would have that little biscuit right here on that soil probe, and that allows us to get this constant depth, because it's more important than you think. being off by a half inch or 1 inch will really change your soil test results. So we put a lot of effort in hitting the exact same depth every time we put that probe in the ground, because in especially something like pasture, your soil properties are going to be stratified. So if we look over here, all that organic matter is up at the surface. And every time I fertilize, phosphorus doesn't move downwards. So that top 1 inch is going to have really high soil test P. And our soil test is calibrated for that. So we designed the soil test for no-till at 4 inches, that we understand it's stratified. But if you push that probe in the ground 6 inches, our recommendation won't be right. So that depth is probably the most important thing next to getting enough soil cores. First of all, you got to cover the field. Make sure you're getting from one side of the field to the other. Number two, most important thing is the depth of that sample. Then you mix it up in a clean plastic bucket. I avoid metal buckets because of contamination, particularly anything when galvanized will mess up your soil sample. Don't use galvanized tools or galvanized buckets. I like just clean plastic buckets. Don't sample when it's soaking wet like this unless you're doing research. And if you do have to take a wet soil, because it seems like it's rained every day in the past 5 years. So I understand. But don't put the soil in the oven. Don't leave it on the dashboard of your vehicle where it's going to heat up in the sun while it's soaking wet, because funky stuff starts happening. If you have to dry it out before it goes to the lab, because that's the first thing that happens when it goes to the lab is they dry it out. But if it's going to be a while before you can get it to the lab, you can spread it out on brown paper or something like that and let it air dry, put a fan on it. You never want to hit it with heat because it'll really mess up the potassium numbers if you hit that soil sample with heat. Make sure that you fill out the submission form correctly, because that's what your recommendation is based off of. As far as timing, the best time to take a soil sample is now. If you haven't taken one, get it done as soon as possible. I prefer the fall because soils tend to be a little bit drier. It gives me the winter months to kind of get some things taken care of, to think about buying fertilizer for the spring. And the labs aren't as busy. The labs are slammed in the spring with soil samples. That is their busy season, and that's how mistakes happen. So for me, the fall is a better time to sample. But the most important thing is be consistent. Don't take it in the fall this year and in the spring, 2 years from now, because you can't compare a fall sample to a spring sample, because potassium changes with the season. As that soil warms up, the potassium goes up, and as it cools down, it goes down. So that timing, just be consistent year to year. If you're a fall sampler, always be a fall sampler. If you're a spring sampler, always be a spring sampler. So I'm going to look at the chat here for a second. Okay, a few people have had some experience with that advanced cal or that pro cal. So no question about food plot and using that advanced cal. I wouldn't waste my money on it. I don't think it helped the neighbor. I don't think it provided any benefit. Our soils have plenty of calcium. The most important thing for food plots, and I do a lot of food plots myself personally, soil pH. Get your soil pH right for whatever crop you're planting in that, and that advanced cal is not going to help you there. I heard that 0060 equals 12 pounds of K and 48 pounds of salt. Is this true? So potassium chloride. So 0060 is potassium chloride. It's a salt. Every fertilizer is a salt. There's some people out there that talk about using potassium sulfate to get your potassium instead of potassium chloride, which is 0060. The problem with potassium sulfate is you're paying for that sulfate that you probably don't need. It's about 10 times more expensive for potassium sulfate. So potassium chloride, which we call muriate of potash, we call it muriate of potash, MOP, or just potash, or 0060, is fine. At agronomic rates, that salt is not going to, it's going to wash right out. Enough rain, we don't have to worry about that salt damage with that 0060 at agronomic rates. So don't worry about that salt. So 0060, let's talk about this for a quick minute. It's a really good question. So that fertilizer bag label, 0060. The first number is percentage on a weight basis of nitrogen. So urea is 4600. So that means it's 46% nitrogen, right? So, you take 0.46, there's 2,000 pounds in a ton. So 2,000 pounds times 0.46 is 920. So there's 920 pounds of nitrogen in 1 ton of 4600. When you look at potash, so potash is 60% K2O. We use oxide equivalents for K. For P, that second number, we use P2O5. It's just an old way of doing fertilizer. P2O5 isn't even really a real molecule. It's just the way fertilizer is labeled. So 0060, a ton of 0060, 2,000 pounds per ton times 0.6. And so that's going to be 120 pounds of potassium per ton. 100 pounds of 0060 is going to have basically 60 pounds of potassium. And so if your soil test calls for 60 pounds per acre of K2O, then you're going to have to apply 100 pounds of 0060. pH is 70%, 70% base. So pH, so percentages would be for base saturation. So your pH would be a number like 7.0 or 7.1 or 6.5, something like that. When you have that percentage on there. So that would be your base percentage number, which I don't worry too much about. CEC of 20. Okay, so it's a heavier soil. Anything over about 10 or 15, I think of as being a little bit clarier soil, good fertile soil. Which source of phosphorus to use? So when it comes to phosphorus, and we'll talk about this in a minute, MAP or DAP. To be quite honest, I'm going to pick the one that is most cost effective. I'm not going to run DAP next to new seedlings in furrow, but outside of that, I'm going to look at what my soil test calls for. Let's say it's calling for 120 pounds of phosphate per acre. I'm going to pencil it out and see which is per acre the cheapest cost. Usually we can get MAP most easily around here, so that tends to be the cheaper source, but they're both fine. You're going to get more nitrogen with the DAP and in a hay production. I actually think in that late summer application, if you're going to make an application in the late summer, surface applied urea, we can't get very much ammonium nitrate anymore. So surface applied dry urea 4600 is going to volatilize. It's going to gas off in the late summer on the surface. Unless I get rain on it within the first 24 hours, I'm going to lose a lot of my nitrogen to the atmosphere. So I'm losing money. DAP and MAP won't do that. So that's a good time to get your phosphorus down in that late fall, late summer, because it gives me a protected nitrogen source to stockpile, particularly in fescue, for the winter, because that DAP has a little bit higher nitrogen. But again, a lot of it comes down to availability. So let me get my chat box closed so I can see my slides. Okay. A little bit about philosophy here. Low testing soils, we expect UK, this is our philosophy of low, medium, and high. And low, we expect a yield response to added fertilizer. And you're going to need a lot. A medium testing soil, your yield response is going to be small to none, but we're adding a maintenance recommendation, because we don't want to fall into the low. So we're putting on what we're removing in that medium range. High testing soils, you're not going to get money back. Your soil can supply it. Don't worry about it. Okay. Now, folks will say, hey, UK, your recommendations are a lot lower than the other soil testing labs. Well, we're all running the same test. We're all running the same chemistry, and we're all pretty much abiding by the same kind of lab. There's these external groups that test labs to make sure that the lab procedures are correct, and everyone's part of those lab groups. So the difference in the recommendations comes down to the philosophy. And so, this is some stuff that Edwin Ritchie did. He sent a soil sample off to University of Kentucky, Waters, and A&L back when it was A&L. Now it's something different. And the same soil, and the soil test results came back phosphorus 84, 79, or 94 pounds per acre. And so you go, oh, 79 to 94 is the range. That's a 14 pound per acre swing or 7 ppm swing. Well, 7 ppm, that's parts per million, is not much. So basically, all the labs got what I consider pretty much the exact same number from 79 to 94. Look, I wasn't smart enough to be anything other than a soil scientist because this is what we call bucket science or tailgate science. It's kind of like horseshoes and hand grenades, close enough counts. And so 79 to 94, 7 parts per million, not a big difference there. On the potassium side, 234 to 270. Again, when we look at the variability in soil tests, basically all three labs got the same number. Now, look at the recommendations. For those same numbers, UK is saying no phosphorus needed, but Waters and A&L were saying 85 or 60 pounds per acre. So they're basically putting out a maintenance rate, even though we're way above where we expect to have any response. For potassium, UK was saying you need 40. Waters was all the way up at 125. So that's 3 times what we recommended. And A&L was 2 times what we recommended. I'm not saying the recommendations are wrong. I'm saying their philosophy was different. There's a lot of variability in crop response. And what they're looking at here is, as a private lab, is they're saying, we're going to make sure you don't come up short no matter what. Whereas we're looking at and going, we've never seen a yield response to phosphorus at 84 pounds per acre soil test. I've spent my whole life studying phosphorus. That's my area of expertise. If your pH is right, you are not going to have a yield response at these soil test levels. Just plain and simple. But they're making a maintenance recommendation that's kind of a just in case. I'm not a just in case guy because that's a lot of money for just in case. Same for the potassium. So it's just different philosophies. Nothing wrong with that. It's just, different strokes for different folks. Let me look at these questions here because now we're starting to get a little chat. I like that. I like the questions. It's better than me sitting here droning on over slides. What time of year is recommended to fertilize? All right. So if we look at what time of year to fertilize, we're going to talk about this a little bit later in the presentation. Nitrogen, we own a pasture. We like to kind of split up and spoon apply during the time the crop is growing. Nitrogen doesn't hang around. So I need to apply it when the crop's growing. Otherwise, I'm wasting my money for the most part. Phosphorus and potassium, different story. I don't want to rut up a field. So I want the ground to be a little bit dry, firm, set up so I can get across it. That's one consideration on timing. Potassium helps a crop be winter hardy, and we're going to get into this a little bit more in the potassium, so I don't want to talk about it too much now. But we get luxury consumption when we apply. If we need a lot of potassium, which again, in pasture and hay, that's the number one need I see. And so if you're going to try and meet that need for potassium, you don't want to put it down in a hay crop before the first cutting, because all that potassium will go straight into that first cutting and go out the door. And it causes dietary issues with the animals. And so with potassium, I'm going to, if I have a really high requirement because my soil test was very low, I'm going to put it down in a split application after the first cutting and going into the winter. And I'm really going to bulk it up going into the winter and the fall. And the reason I say that after that last cutting is potassium is really important for winter hardiness. So if I've got a really low soil test, by going into the fall with it, it helps me in 2 things. 1, it helps that crop survive the winter. And 2, I don't get the luxury consumption because it gives the potassium time to work into the soil CEC, and then it'll leak out to the crop over the next year. Wouldn't 0060 have 1,200 pounds instead of 120? Well, I'm not going to say that my math wasn't wrong because I'm not a math wizard. So, but it's 60%. So I'm going to take 0.6, and a ton has 2,000 pounds. So 0.6 times 2,000. I'm using a calculator here. Is 1,200 pounds. Good call, Philip. So this is what happens when you do stuff live and you don't check your math. So 1,200 pounds, 0.6 times 2,000 is 1,200 pounds per ton. All right, let's keep on going down. Last year, we did soil samples for the first time. and went exactly what the recommendations were. The pasture last year did not produce nearly as good as before. Is an old strip mine in Eastern Kentucky. What would you recommend to do this year in the spring? If it's an old strip mine, you're going to have catching up to do. We're going to get into this in a second. We're going to talk about that buffer, that reserve in the soil. These strip mines, I spent 2 years testing strip mines before when I was doing my postdoc after I finished my PhD. I worked at Virginia Tech, and I spent 2 years living on strip mines in Eastern Kentucky. And, there's a lot of fertility problems out there, and it takes a long time to turn those soils around, because what you've got is basically they brought that overburden back in there, and you don't have a lot of organic matter, and you've got poor fertility. You usually have some pH issues, and so my focus on those is going to be the pH and getting a really hardy crop out there, because the way you turn the organic matter around is by growing a crop, because 50% of your crop's weight is in the roots. The roots is what builds that soil organic matter. And so you need a really strong rooted crop, rye, things like that, fescue if you're really trying to grow pasture and hay. And I'm going to focus on the pH. I'm going to focus on the potassium. If the potassium is good, then I'm going to start investing in the phosphorus. But the pH, to get a good, strong rooted crop growing out there. You can have micronutrient issues on those reclaimed mine soils. Again, I stay away from them in general. Fertility, I don't worry about it, but you might want to look at those numbers on the soil test. It takes a long time. If your soil test phosphorus is low, you can apply to move. So a soil test that tests 5 parts per million, it would take 6. So 5 parts per million is 10 pounds per acre soil test P. If I wanted to move that 10 pounds, so I wanted to move from 10 to 20 pounds soil test, it would take 600 pounds per acre of P2O5. Now, clearly that's cost prohibitive. So our recommendations only go up to 120. So it's going to take many years of applying that very high rate to move the soil test up. And that's because it's that iceberg that we described before. It just takes a long time to kind of push that up and move that buffer capacity. Scroll down here. Is it okay to spread manure on hay fields right now? Let's see. It's March. Well, right now, it's a little wet. I wouldn't want to be running across the field. Compaction. When I was a young man, I worked on a farm before I went to college. They actually paid for me to go to school. It was a farm that DuPont owned. And the man that I worked for is a smart man. And he told me that compaction was the number one worst thing we did to limit production in our fields. That's man-made damage. And I believe it's true. And so right now it's really wet. In the winter, you're not going to get as much loss of the nitrogen right now because it's cool. So it's not going to mineralize. So I'm not too worried about that as we move in. I wouldn't want to put it on in the fall per se, late fall when the soils are cold, because that nitrogen is going to be sitting there all winter and denitrifying. But, once the soil dries up, if you can get across that field, we don't recommend applying on frozen ground because you get a lot of runoff, which has environmental impacts. But once I know it's a slow waiting for things to dry out, but my biggest concern of running across ground right now is how wet it is, and how's that soil going to hold up to that traffic? Because a little bit of compaction, you'll be paying for that compaction for 20 to 30 years. It just doesn't go away. Boy, we're getting a lot of questions. I like this. Am I understand that we pull 12 to 20 plugs per soil sample, but only about 1 teaspoon is used for testing? If so, how does all the plugs get represented? That's exactly right. So get those plugs in the bucket and crumble them up and mix them. Now, when that sample comes in the lab, what's in the bag, they crush it up, mix it up, and take out what they're going to sample, right? It goes through a sieve, through a grinder, and gets mixed. But what I do is I put those 20 plugs in a bucket, and I get in there with my hand and I crumble them up. And I want a little bitty piece of every one of them plugs to go in the bag. I crumble it and mix it up myself in the bucket. Takes 1 minute, 30 seconds. I get in there with my hand. I crumble those plugs up, grab a handful, throw it in the bag. Because you want to make sure it's just as thoroughly mixed as possible so that every plug gets a little bit into the sample that gets used. There's no way around it. It's just got to be well mixed. Let me see here. Follow-up question. So what grass do you recommend to plant on strip mine that would be best for pasture? That's a hard, fescue tends to be a pretty strong grower. That's my standard go-to for most situations. If we get the pH right, get enough nitrogen on it, it's going to produce a lot of biomass. It's hard to beat. Some people, if they're really having trouble getting a stand established, cereal rye, again, you're going to have to replant every year, right? But it makes, I don't recommend ryegrass because it becomes a weed issue. So there's people that really advocate it. It's a super strong grower. If cut at the right time, it can be palatable. But it can also present a weed challenge, especially for your neighbors that they might not like you too much with that ryegrass. But if you go with cereal rye, if you absolutely can't get anything else established for a couple of years, just to help break up that pan and get some organic matter in the soil, it can be cut for hay and be relatively palatable if you don't let it go too long. And to be quite honest, that's a really great question for someone like Jimmy Henning, because I'm a soils guy, not a plant guy. I mean, obviously I work with plants, but I'd be interested to see if they agree with what I'm thinking there.
Hey, Keith, we'll follow up with that question on the 22nd with Dr. Smith.
Yeah. Oh, Ray.
Remember and ask him that one.
Yep. Ray's got a ton of experience. He was actually at Virginia Tech when I was there. So he's got a ton of experience with those strip mines. Yeah, absolutely. All right. Let's keep on chugging along, man. I love these questions. If we don't cover all the slides this evening, I'd be happy. I don't like boring you all with slides. So I love the questions. Just how do we make those recommendations, and why I say there's some, a little variability in there. And so there's different philosophies. This is how we make recommendations. And we're constantly doing this. I'm working on this with phosphorus right now for Kentucky, checking our recommendations. We go out to a bunch of fields with a bunch of different soil tests here on the horizontal axis. All these fields have different range of soil tests. Let me get back here. Click there. So you got all these fields with different soil tests and relative yields. So that means I've got two plots side by side, two little patches, and I put fertilizer on one and none on the other. And then I cut that hay, and I divide the unfertilized yield by the fertilized yield. So I'm going to do the math easy. I get 100 pounds fertilized, 50 pounds unfertilized. Relative yield is 0.5. All right. And so the lower the soil test, the lower the relative yield. As soil test goes up, I get close to 1. We usually use 0.95 as a cutoff. And I say, okay, from here on up, I don't need fertilizer because my unfertilized plot and my fertilized plot got the same thing. So everything below there needs fertilizer. And we do this for all the nutrients, right? So that's correlation. Calibration. Now I know the soil test point where I need fertilizer on average. Now, I want to back up here. I'm going to show you something. Notice there's noise, there's range, and this is fake data. That's not real data. I drew this picture just to be clear. Real data is really noisy. And so this point where we say above there, I don't need fertilizer, below there, I do need fertilizer. That's actually, it's not a point. It's more like a range. And, it's an average. And so that's why that history of soil test for your field and what's happening with your field, is your soil test going up or going down for P and K? And we know with hay that if you're applying 1010 or 19, your K goes down and your P goes up. And that's why we have problems in hay crops. And so you've got to get a custom blend if you can to match your soil test, because you can get a whole lot more K, and phosphorus is expensive. No sense in pouring all that money into phosphorus if your soil test is up there in that optimum range. So then we go out and we do calibration. So for calibration, we step back and we say, okay, I'm going to go out to a bunch of fields, but now instead of just single rate. I'm going to put multiple rates out. So now instead of soil test, the horizontal axis is fertilizer rate, whatever nutrient we're looking at. And we look at yield. In this case, this slide, I have bushels per acre. And so if my soil test, this gray line, I say soil test 10. As I add more fertilizer, yield goes up until I hit a maximum point. Soil test 20. So this field's a little bit higher. I add a bunch of rates, yield goes up until I hit a maximum. So as my soil test goes up, I get to the maximum with less fertilizer. Soil test 30, I only needed about yay much fertilizer to get there. So I needed more fertilizer for the orange field and even more fertilizer for the gray field. One of the things that's important to point out is even on a low fertility soil, I can kind of get to maximum yield, all other things being equal, just by adding some more fertilizer. So my plant's living off of the, a plant takes up potassium from the soil and from the fertilizer. The higher the soil test, the more of that nutrient that's coming out of the soil versus from the fertilizer. So that's correlation. Here's calibration. That's how we come up with our recommendations. That's the same. None of the private labs are doing their own correlation and calibration that I know of. They're using university data, from the old days for this information. But just because I maximize my yield at this fertilizer rate, that doesn't mean that becomes the recommendation. This is just the data that goes into the recommendation. Then they have this philosophy. And so there's the sufficiency, there's the build and maintain as a hybrid. And almost everyone's in the hybrid, right? But then it's a spectrum. And so UK is closer to sufficiency because it's more of an economic model. Some of the private labs are going to be closer to build and maintain because they're risk averse. They aren't worried about what your fertilizer bill is. They're just worried about how green the crop is. Whereas UK is trying to balance fertilizer bill and how green the crop is. And to be quite honest, our recommendations, everything I'm seeing, I run these tests in grain crops, but working on this stuff with Dr. Henning in hay fields with potassium, our recommendations are higher than they need to be. We have insurance built into our recommendations. I know people laugh at that and they go, no way, not as low as yours are compared to somebody else's. Our recommendations are higher than the sufficiency approach. All our data indicates that. So we're recommending more than you absolutely need, because the sufficiency approach is just exactly what you need this year to maximize yield. And with the sufficiency approach, you fertilize every single year and you soil test every single year, and you never try and build at all. We have a little build component. And so that's what this chart shows over here is what I was telling you earlier. This is some data from Kentucky, and that blue line is fertilizer rate on the vertical axis and the initial soil test P, and how much fertilizer do I need to move my soil test 10 units in 1 year. And this is our recommendation for corn. And so you see for our phosphorus recommendation, we stop at 200 because trying to rapidly build is a waste of money. And so this is where we move off of that build and maintain. The actual sufficiency rate in this soil test range is about 60. So we're recommending 200. The yield maximizing rate is between 60 and 100, depending on your soil. And we've put a little insurance in there to try and get you built up a little bit. And then we get closer to our known sufficiency as we come down here in this mid-range, and then we cut down to 0. So those are our corn recommendations on that slide, but just for reference. All right. We're in the home stretch here. I'm going to check the questions again. Is there any research indicating normal commercial fertilizer has negative consequences as organic people think? I love that question. Let's see the other one here. Perfect. Well, if you have field fertilized correctly, what is the rough maximum of tons per acre of hay? All right. Is there any research indicating normal commercial fertilizer has negative consequences? The poison is in the dose, right? No. Fertilizer is fertilizer. Plants only take up inorganic nutrients. So they take up nitrate and ammonium. They don't take up organic nitrogen. But when we apply manure, that organic N mineralizes quickly to nitrate and ammonium, and that's what the plant takes up. So it's getting the same thing as it does from fertilizer. P and K, same way. They can only take up phosphorus as an inorganic phosphate molecule out of the soil solution. And so the organic phosphorus in manure has to mineralize. Potassium is already inorganic in manure. Most manure potassium is potassium sulfate. There's some other potassium compounds in there, but it's all inorganic compounds. And so there's, from the plant's perspective, no. Now, am I applying salts with fertilizer? Yes. If I over apply, can I damage my soil? Yes. But in any meaningful way, if you're applying the right rate of your nutrient, the source just changes how you manage it. I love manure. I use a lot of manure. I grew up on the Delmarva, Delaware. Lots of poultry production, lots of poultry litter. It's a great nutrient source. Absolutely nothing wrong with it. It's not magic. There's nothing magic. There's a fertilizer being sold now that has, they're like, oh, we have organic stuff in it. And it's super expensive. To me, it's dollars per acre to get my fertilizer where it needs to be. There's nothing magic. Organic matter is good. You're adding a little bit of that. You're not adding a lot. You won't really change your soil organic matter. But there's nothing wrong with inorganic fertilizer at respectable rates. Rough maximum tons per acre of hay. That's a tough question. I'm gonna stay away from answering that because it really depends on the soil. In my opinion, when you take care of your soil fertility, at that point, your yield becomes a question of water availability, which has to do with soil texture, soil depth, and the amount of organic matter in your soil. So some fields, the best that they might be able to do is, I just jumped all over. I just hit a key here and you got me so excited with the organic question. I jumped all over the place in my presentation. Water availability is where it comes down to. So at the end of the day, a bad soil, maybe you can only do 1.5 tons or 2 tons per acre. But, I've seen people pulling alfalfa off, north of 6 tons per acre on tremendously deep soils, right? So like deep topsoil. And so it just really depends. And so I hesitate to give a definitive answer. Let me see here. On liming soil with a CEC of 20, I have heard CEC times 400 times 0.75 equals 6,000 pounds of calcium. What do you think? So I think a lot of people reach too far with CEC. So CEC is calcium or is cation exchange capacity. And the heavier soil it is, the more exchange sites, negatively charged sites for positive cations to attach to. Most of these equations like that aren't very good because there's other variables other than CEC. And in fact, none of the soil test labs actually measure CEC because it's difficult. So we estimate CEC based off of other properties. It's not a true measurement of CEC. So most of those equations, they might get you close, but we have plenty of calcium in our soil. You never, ever have to worry about calcium unless something's really messed up. In which case, give Philip a call and we can have a conversation. He can get you in touch with me if something's really, really jammed up. But I don't worry about CEC other than I look at it and I can tell if a soil is heavier or lighter, and that's about it. 20 is a heavier soil. I'm going to need a little bit more lime to move the pH with the CEC of 20. But actually the buffer, so that lime requirement, that Sakura buffer, it is designed to determine the CEC effect on lime. So we don't even have to worry about the CEC because I've sent it to the soil test lab. I got my Sakura buffer pH back, and that tells me everything I need to know about the CEC. What is the typical analysis for cow manure? It's variable. Dry stack cow manure. It could be, I've seen it high in nitrogen or low, depending on what the bedding material is. The more carbon you have in the bedding material, the nitrogen can go down, but you can have 3 to 4% potassium and 3 to 4% phosphorus. I've seen them where they don't have, depending on how it was stacked and everything like that. I've seen it run, 624. I've seen it run 2 3, 6, something like that. It really depends. You can get them analyzed. I recommend having manure tested. That way you know what you're applying. All right, let's take a look here at where we're at in the presentation. All right, I'm gonna let's get into this P and K here because I do want to cover a touch bit of this here. Hay and pasture P and K management, soil testing, we covered that. Follow your soil test. Luxury consumption of K can be a problem, particularly in alfalfa, more so, but any of the crops. You don't want to apply your potassium, as I mentioned before that first spring cutting. Your K will be removed because as the crop is growing rapidly in the spring, that's when we get the biggest flush of growth and the biggest nitrogen uptake. So that plant is the way it takes up potassium, about 80% of it is through this like transpiration stream. We call it mass flow. So as the plant transpires water out the top, it's sucking N and K in through the bottom. That's different than how it takes up phosphorus. And so as it's growing really fast, it can pull up all the K you applied that's really soluble and they're in the soil from that fertilizer. And then you're taking it off in that first cutting. I mentioned this, so I'm not going to talk about it other than just to, kind of highlight it again. pH, pH, pH. That's going to control your phosphorus availability. Phosphorus moves very short distances, so you need good roots to get after it. Sometimes when we see phosphorus deficiency in the spring, we actually just need a couple of warm days because also phosphorus moves more slowly when the soil is cold. Phosphorus availability, crops only use about 10 to 30% of any phosphorus you apply per year. The rest goes into the soil storage and then gets used in later years. There's this huge kind of buffer capacity for soil and phosphorus, and we're just kind of cycling it. In pasture, your timing options are limited. We are worried about phosphorus from an environmental standpoint. So putting out a bunch of phosphorus right before a big rain isn't the best for your streams. We worry about wet soils and compaction. Cost of fertilizer, availability of equipment. These are usually what determine when and how we apply phosphorus. Most ag soils would naturally be low in phosphorus, but many years of application of triple 19 usually jacks the phosphorus way up, and you can just save that money and stop applying if your soil test phosphorus is high. And that's what we see with triple 10 or triple 19. I see a question popping up here. Proper range for P and K. What was the range for soil test K? All right, for hay crops, for soil test K, we're shooting for 270 to 300 pounds per acre soil test K. Soil test P, 50 to 60 pounds per acre. So that's where we're trying to get to. And hey, I've seen soil test K and hay crops down in double digits, like 20, 25. And you're going to have trouble growing a crop if that's where your K is. And that's what happens when you apply something like triple 19 for 20 years straight. Potassium, I'm not going to get lost in the weeds on potassium. Potassium is very complicated chemically. It interacts with the clays in our soils. It can get sucked into what we call the inner layer. Clay looks like a sandwich. And so you have these two flat layers and K can get shoved in between there. That can be a problem. I don't want to waste time talking about that. It moves a little bit more down through the soil than phosphorus, but not as much as nitrogen. So leaching is not as big a problem, particularly in our soils. So I'm not worried about leaching of K like I am with nitrogen. With K, after the first cutting or the fall is the best time to apply it. If you have a really high K requirement according to soil tests, split apply it. So after the first cutting and in the fall. Again, I mentioned all this before. Manure K is equivalent to fertilizer K. So that's a thing. Let's see here. Question. I've been told liquid boron applied to urea potash for alfalfa is more effective than granular boron due to the low application rate. Thoughts? Boron's tricky. Actually, I'm doing a boron study in soybeans and corn. I did last year and doing it again this year. And so there's all kinds of different ways to apply it. I guess I would go with what's easiest. The problem with boron is you're applying such a small rate. with a granular product, sometimes distribution in a hay field can be problematic, whereas with liquid you can dilute it and get it spread out. But I don't know if I'd worry about it too much. um, Boron, I'm more worried with boron about over applying. So boron's one of those things, particularly in alfalfa, it tends to be sensitive to boron. If you're short, you'll notice it. If you over apply it, you can really damage the crop. And so it's a trade-off. The liquid boron, it's a physical characteristic. It's not that it's better. So we looked at the numbers. We did tissue sampling and stuff this year, and the liquid stuff is a little more soluble, but some of the granular products were actually more soluble than the liquid. But at the end of the day, where you're applying, pretty small rates of these products, getting the distribution can be problematic. And so that's where the liquid might come in. It might just be handier to apply. But again, it's such a small problem. If my pH is right, but I do need boron because I've seen a deficiency or whatever, I'm probably going to use the cheapest per acre solution to get there. And it's, boron's really soluble, so the rainwater will distribute it through the soil pretty quickly as when it rains. So I'm not really worried about it. I'm going to look at, to get my rate of boron that I need per acre, what is my most cheapest way, and part of that consideration is what equipment do I have available. Luxury consumption, we talked about this. Split application and not applying before the first spring cutting. That's luxury consumption. And the reason we worry about this, not only because we're hauling off all that potassium, but because high soil K can result in that high forage K. And so when you have excessive soil K levels, you get luxury consumption, or you apply too much fertilizer for the first spring cutting. Then you have these high feed K levels, and you get a mineral imbalance. And so you end up with too much K versus the magnesium. And so sometimes I'll get calls where people want to apply magnesium, like Epsom salts or something out in the field, because the forage K is too low. That's not the solution. That won't work. You're going to have to use a feed supplement to get that K back, the magnesium back up relative to the K. You're going to have to supplement the rations. Fertilizing the soil with magnesium won't help with, milk fever or grass tetany. I see another question. Let me pull that up. Yes. So a great question. So I understand it's best for nitrogen needs to keep my legumes above 30% of the forage. Is this true? Yeah. So, our nitrogen recommendations are based on what percent of your field is legume. So legume can use N2 gas out of the atmosphere, and soil has its own atmosphere. There's air in the soil. And so they fix nitrogen. And if your pH is right, particularly your legumes are going to do a good job with nodules of fixing nitrogen. And they help feed the grass that's in that mix. Now, how do they do that? I've heard some people ask about, well, does the grass root have to touch that nodule? No. The way they do it is they, that plant material that they drop, the dead leaves, the stems, the root material that sloughs off as that root grows through the soil, it's dropping dead cells everywhere in the soil, is higher in nitrogen content and has a low C to N ratio. And so it mineralizes. And so that legume helps to feed that grass. So yes, keeping that up above 25%, I think, and you're going to have plenty of nitrogen typically. So yeah, great question. Soil test pay, I already showed this data, so I'm not going to go into it a lot. But when your soil test is low, I've had people tell me, look, I've been applying 120 pounds of phosphate every year for 10 years and my soil test hasn't moved. It doesn't surprise me if your soil test is in the single digit range for phosphorus. Potassium is not so bad. If your potassium gets low, it's more linear. So if we look at phosphorus, so this was initial soil test, pounds of P2O5 per pound of soil test change. And so you see it's non-linear, right? Real high at the low soil test, real lower rate needed at the higher soil test. But when we look at soil test K versus adit K, how much it changes, with K, it's more linear, so it's not as bad. Back to that boron, apply 1.5 to 2 pounds of boron every other year for hay and pasture. This tends to be kind of a general recommendation, but if soil test boron is over 2, do not apply. If your soil test boron is under a 0.5 pound per acre, you're definitely going to need that boron. If you're in that range between 1.5, 0.5, and 1.5, that's where I'm going to worry about applying some boron. Just kind of general. Make sure your pH is right. You're not going to need that boron as much if you get your pH is right, but that boron is for these high tonnage situations. I said this before, fertilizing with magnesium doesn't help with grass tetany. And nitrogen volatilization. Now, this is something that came out of conversations with Jimmy Henning. Dr. Henning, if you need phosphorus, if your soil test calls for phosphorus, use DAP or MAP in that late summer because they're non-volatile, which is a problem in pasture. When you apply urea on the surface, it's a pasture, you can't work it in. You get volatilization if the soil temperature is above 45 or 50 degrees Fahrenheit. So those spring and summer applications with warm soils, you got 2 choices. Apply that nitrogen before a gentle soaking rain. You don't want it before a mudslinger when it's all going to run off. But that nitrogen before gentle soaking rain will incorporate the nitrogen, won't volatilize. Or use DAP or MAP. Or you can use something, a chemistry like NBPT to treat your urea, can also help prevent some of that volatilization. Okay. Now, nitrogen management, it's getting on late here in the evening, so I'm going to kind of cruise through the nitrogen management because it's not a big deal. But the nitrogen cycle has a lot of movements in it. It's very dynamic. Nitrogen moves around in the soil. It changes forms every couple of minutes. And so we don't soil test for nitrogen. There is no soil test for nitrogen. So we're balancing plant need and fertilizer. How much does the plant need? What's the soil give me? Again, we don't have a soil test. We just kind of estimate this. And what's the efficiency of my fertilizer? And, so we're trying to balance out these different kind of components to come up with a nitrogen recommendation. The efficiency of this fertilizer becomes very important in a no-till system like hay or pasture. If I'm applying urea, as I said, if it's 80-degree air temperature and humid and a gentle breeze blowing, 50% of that urea is going to blow away as gas. And so there are some options to stabilize. Again, DAP, MAP don't do that. Ammonium nitrate doesn't do that, but we can't get ammonium nitrate anymore. Ammonium sulfate doesn't do that. Just, urea or UAN, half of the nitrogen in UAN, liquid nitrogen, is urea. So half of it is at risk. The other half of it is ammonium nitrate, so it's not at risk. So with liquid nitrogen, streamer nozzles are a good way because you put it in a concentrated band, you don't get that volatilization as bad. NBPT, one of the original commercial names was Agritane. It's off patent now, so you can get it through a lot of other products, but you're looking for that chemistry. NBPT can limit volatilization. There are polymer coatings. They're more expensive sometimes, but like ESN is a commercial one. I can't think of the other name of one right now, but it's basically polyurethane coating on the prill, and it breaks down with moisture and kind of releases the nitrogen. The reason we don't apply nitrogen in the fall, or we try not to in the late fall, is because our soils are wet over the winter, and that nitrogen will either leach away or denitrify. And so nitrate can denitrify into a gas. So that's different than volatilization when soils are saturated and there's no oxygen. So there's 2 chemistries, DCD and nitropyrene, that do a pretty good job of keeping that from happening. But the better option is, you might need that in your spring application when the soils are really wet and you're getting ready to go in that growth. But for the most part, our soils aren't saturated except for in the winter. So, we don't need to be putting nitrogen down in December. Here's the thing about the legumes with the question. Here's a clover orchard grass mix, fertilizer, nitrogen added across the top. How much dry matter was harvested? This is John Grove gave me this slide, and this is some Kentucky data. And we see that we got more grass production with more nitrogen added, but less clover, because as we added nitrogen, the grass was able to outcompete that clover. And so we actually got the highest tonnage when we had the most clover and no fertilizer, right? So we got 7,300 pounds per acre of dry matter with no fertilizer. And we actually went down because we suppressed with that high fertilizer nitrogen, we suppressed that clover growth. So that gets back to that question we had. So timing of nitrogen, late winter. So we're looking at it now, February 15th to March 15th, trying to get out there before that crop breaks dormancy. We can go up to 100 pounds for our recommendations in cool season grasses. Again, right now the soil is pretty wet. I wouldn't want to be trafficking it. Then that early summer up to 50 pounds. And that late summer, particularly if I want to stockpile and get a lot of growth. If less than 25% legume, follow AGR1 recommendations for grasses. More than 25% legume, you can cut out that nitrogen. Urea-based fertilizers, I've beaten that one to death with the volatilization. You either got to incorporate it with rain or steel. Don't put urea down right after lime. That's an important point. The pH from that lime application can cause some volatilization issues. So we're going to bring it on home here with a quick thing about nutrient removal and cost of production, because I always get this question when we get to hay crops. These are a little bit older fertilizer prices, but I don't think they're too bad. But you can figure this out. If you know how much crop you're pulling off, here's some book values that fescue takes off about 35 pounds of nitrogen per ton, 18 pounds of P2O5 per ton, 50 pounds of K2O per ton. Clover is 41, 11, and 54. And then we look at what's the price. Well, urea, if we use urea, 320 a ton, 35 cents a pound of nitrogen, that's probably a little high right now. DAP is $400 a ton, 30 cents a pound of P2O5. And potash about $400 a ton, 33 cents a pound K2O. How long should you wait after applying lime to apply urea? There's no solid rule of thumb. I know you're going to hate this answer, but as long as possible, but not so long that you come up short of nitrogen. It's really a timing issue. So if you apply your lime in the fall, I think that's a good time because your winter freeze thaw cycle will work the lime in. So if you're doing a single application per year, you're not going to be applying nitrogen then, and it won't affect your DAP or your MAP. And so in the spring, if you do have to get some lime out there, I would put down if you're forced that you got to put urea and lime out at the same time, get your urea out first, wait for a rain, then get your lime out, because or give it a little bit of time for that urea to work in the soil, because even the dew will dissolve that urea prill. It'll soak into the soil. Once it gets in the soil, it turns to ammonium and it clings to the soil, and you don't have a problem. So if you have to apply them at the same time, get your urea out first and give it a week or two to work into the soil. So here's our nutrient values. I know potash has gone up a little bit here due to some, different price fluctuations with potash is kind of funny. And there's a lot of kind of crazy things going on in the market with availability and China buying grain, and grain prices go up and potash prices are pegged to grain prices. And so we've seen some fluctuations in the fertilizer market recently. But this is an easy way. You can kind of do this math on your own for whatever you're paying for fertilizer to kind of figure out. It's a little tricky to figure out what the price of that phosphorus is, because you got to tease it out of DAP, which is 18460 or MAP, if that's what you're getting. And the way I tease that out is I take and figure out what my nitrogen is based on urea, and then I take my nitrogen value out of the DAP and figure out what's left for my phosphorus. It's a little bit complicated, but and so if you got 2 tons per acre of fescue, you're taking out at those prices about $25 of nitrogen, $11 of phosphorus, $33 of potassium. So almost $70 per acre of fertilizer that you're taking out. And so, what's your fertilizer bill versus what you're removing? 3 tons per acre, it's about $100 per acre that you're growing. And so, you're kind of looking at the trade-offs, and it's just the cost of doing business. Now, if I throw clover in, actually my removal is a lot less because I'm providing nitrogen into the system, right? It's not a cost. I'm not pulling it off. And that's why having those legume grass mixtures is so valuable. But this is just something I kind of throw into the slide set because typically people ask me a question about this. I'm always happy to like talk about questions. I love answering questions and stuff. And you can always reach out to Philip and if he's got a question or whatever, we can get together on some of these things. And there's my contact information. I'm on Twitter. I don't do too much on it, but I am on Twitter at NPK Professor. And there's my email address. I'm going to leave that up there for a second. I'm going to look at the questions. Oh, thanks, Dale. I really appreciate that. I really appreciate that. It really means a lot. I'm glad that I love getting feedback because look, if you all tell me that you need different information, the next time the slide set will be different. I'd like to try and put out there what you need to hear. So I really appreciate that. Thank you.
Hey, Doc, I had a
yes,
question that was texted into me. They were having a little trouble with the chat.
Okay.
When you were talking nitrogen sources, what's your thoughts on ammonium sulfate?
Okay, ammonium sulfate is brilliant, right? Getting some sulfur if you need it, which we don't always need. I meant to mention that, and I'm glad you brought that up, Philip, because we're going to talk about soil test sulfur for a hot minute. But problem with ammonium sulfate, it's expensive. There's been some research that's shown that when mixed in with in liquid with UAN, it suppresses some of the volatilization. Ammonium sulfate doesn't volatilize. Great nitrogen source, great source of sulfur if you need it. Sulfur does drive up we've seen that when we fertilize with sulfur, it drives up protein content in the feed. What I was going to say about sulfur is this. Some of the soil testing labs report soil sulfur, and they make a recommendation based off of that. I've done a lot of research on soil testing for sulfur. I've done studies where we've done multiple different chemistries of analysis of the soil. Soil test sulfur can't be used to make a sulfur recommendation. So I come from an area on sandy coastal plains soils. Again, lots of irrigation. 70% of our corn ground's irrigated. And you need to put out 20 pounds of sulfur every other year on your corn ground in that situation. Here, we have not seen consistent responses to sulfur. We've seen spotty responses to sulfur in alfalfa stands, but not a lot, not consistent. Edwin's been doing that work, and Grove has done some of that work. When I'm driving around, I spend a lot of time in the field. I have seen sulfur deficiency. Most of the time, it's related to weather, either compacted soils or cool weather, and we needed a little bit of warm weather, and it grew out of it. You can identify that because you'll tend to see it in spots in the field. Also, sulfur, when it is really sulfur deficiency, you'll see that lighter colored crop. It looks a lot like nitrogen deficiency is going to be on the thinner soils, the ones that aren't as deep. On that side slope that's eroded, tends to be a little coarser textured, not as deep, lower pH, and we tend to see a sulfur need there. So you can't go by soil tests for sulfur. You have to look for that visible deficiency. Look for that visible deficiency, and you can do a tissue test in what you see visibly, take a sample, and what looks good and take a sample. Another way is strip drop. Take some ammonium sulfate and go out there and feed the chickens. Scatter somewhere you see that deficiency, and then take an equal amount of nitrogen as urea and throw next to it. You got to have a comparison because you want to make sure you're not getting that nitrogen bump. But you put your urea down, put your ammonium sulfate down, and if the ammonium sulfate jumps out way ahead of the urea, yeah, that was sulfur deficiency. You identified it correctly. But we can also use tissue tests and use the nitrogen to sulfur ratios. I don't know the hay crops off the top of my head. In corn, I look for 15-to-1 ratio of nitrogen and sulfur. If I get above that, I start worrying about sulfur deficiency, but I can't tell you the hay crops off the top of my head. So ammonium sulfate is great. I think it's probably too expensive to use as your straight nitrogen source. So any other questions? Are nitrogen stabilizers worth it in pasture and hay? If so, which tend to have better ROI? Under what conditions will we tend to get best returns on stabilizers? Another great question. I don't push the stabilizers. I mention what they are so that you know what they are. I don't think they I don't think they pay for themselves in hay and pasture. The only time they would, in my opinion, on hay and pasture is NBPT applied at the proper rate. Some of these products out there don't have enough in the product. Because it's off patent, they put a light load in there to be cheap, and it's not enough. I can't tell you off the top of my head, the numbers escaping me right now, how many pounds per ton they got to add, but I can look it up later. But NBPT in July or August. So if you surface apply urea in July or August and you don't get rain within a day to 3 days, you've lost 50% of your nitrogen. So clearly there, even if NBPT is costing you an extra $5 an acre, it's probably going to save you a little more than that in nitrogen. So there it's going to return, right? Because the other way you can do it is you can just up your nitrogen rate to compensate for the loss. But, sometimes you're just chasing your tail with that. So July or August, surface applied and no rain in the next 24 to 72 hours, NBPT can pay for the investment. Outside of that, I don't see it paying for itself. And the reason I say July and August again is because the warmer it is, the worse the volatilization is. Worst case scenario, warm, little humidity, and a breeze, because the breeze moves that ammonia away so that more can volatilize up. So you got to think about those calls. Is it warm? Is it breezy? And has it not rained? Because rain incorporates that urea. The urea turns to ammonium, and ammonium sticks to the soil. Ammonia volatilizes as a gas. Does nitrogen stabilizer help with leaching in a very wet spring? Yeah, and the bigger loss that I see in Kentucky, because our soils tend to have restrictive layers, so they get saturated. If a soil stays saturated for 3 or 4 days, you get denitrification, and that's actually worse than leaching, and that's where your nitrate goes. So what happens with leaching is you have urea, you put it on the soil, it goes into the soil, it converts pretty rapidly to ammonium. When the soil starts to warm up, so above 45, 50 degrees, and the warmer it is, the faster this happens, but I'm not going to worry about it too much until the soil temperature is above 50. So soil temperature is above 50. I have a little bit of moisture. That ammonium goes to nitrate. And then it rains, and nitrate is negatively charged. Soil is negatively charged, and the nitrate goes down with the percolating rainwater. If that soil stays saturated, so there's no oxygen for 3 days, 4 days, I get a lot of loss through denitrification. A nitrification inhibitor keeps the ammonium as ammonium and doesn't let it go to nitrate. Now, it doesn't work forever. I've done a ton of nitropyrene studies. So that's Instinct for UAN or NSERV for anhydrous. I've done a little bit with DCD, not as much, but it blocks that nitrification for 3 or 4 days. Basically, it's an insurance factor that gives you a couple days of protection, hoping the soil dries down. It's not permanent. But when it's cool in the spring, I don't worry about the nitrification because, yes, I'm going to lose some. Our recommendations account for that. You don't lose more than the cost of the nitrification here. That's why I don't think the ROI is there for hay. Because in that spring, when it's cool, that nitrification inhibitor probably costs a little bit more than what the nitrogen I lose costs. Now, from an environmental standpoint, yes, losing that nitrogen has some impact. And so it comes down to ROI and balancing all the way back to the 4 R's, our objectives. We are balancing environmental because we all want to protect the environment, and we're balancing the cost of that. I just think in the cooler weather, I'm not as worried about it. So in hay, I tend not to focus on those nitrification inhibitors. But, hey, if you're willing to spend that $5 to $15 per acre, it's an insurance policy. I pay for car insurance on all my vehicles, and I never use it, but I still pay. So that's a personal preference kind of thing. Is there a relationship between nitrogen and sulfur in increasing organic matter? Yes. So an organic matter is the primary source of sulfur and nitrogen that the soil supplies to us. And so the ratio is pretty consistent, nitrogen and sulfur, and it mineralizes as the soil gets warm. That's why I said most of the sulfur deficiency we see, we come out of as soon as the soil warms up, because a crop needs a lot less sulfur than it needs nitrogen. So we can't just live off of organic matter for a grass crop, but we can live off for nitrogen, but we can live off of the sulfur and the organic matter for a grass crop. A little bit of warm weather, a little bit of moisture, I'm probably going to get the sulfur out of the organic matter that I need. We also have a lot of sulfur in our soils that hangs up down about 1 foot to 2 foot deep in the soil on the finer particles. So sulfur sticks to the finer particle colloidal matter in the soil, we call it. And so that's the other thing. A couple warm days and I get more root growth and I hit that sulfur band. So when we do soil sample for sulfur, when we're doing research, we take 12 and 24-inch samples, because in Kentucky soils, we see a bunch of sulfur down there. And so once your roots get down there, you're good to go. But yes, nitrogen and sulfur both mineralize out of the organic matter, and the organic matter can typically, 2 to 5% organic matter can typically provide plenty of sulfur to our crops. Again, where I grew up, we have less than 1% soil organic matter, and that's why we tend to see a need for sulfur fertilization. Used to get it for free in acid rain. We've taken care of acid rain by cleaning the smokestacks in our coal plants. Those coal-fired power plants, that's where a lot of the gypsum actually comes from. Calcium sulfate is a byproduct of cleaning. Calcium sulfate is gypsum. That sulfate came out of coal-fired power plant stacks. It used to go up in the atmosphere, come down in the rain. We got it for free. Now we're cleaning it up and making gypsum. We're not getting it for free anymore. Gypsum's a good, sulfur source. It's just what we used to get for free, and now they're capturing it at the smokestack. Any other questions?
We've had some great questions, Doc. I appreciate your time.
Man, this has been a great evening. I'm really impressed by the number of folks and everyone's interest. I love having the questions. So thanks for having me, Phil.
Well, guys, if no other questions are coming in, next Monday night, will be Mr. Tom Keene, and we're going to be talking about the marketing of the high quality hay that we're going to be producing after we learned about being a master haymaker.
Right on.
We're getting wrapped up. So guys, everybody be safe tonight, and I will see you next week when Dr. McGrath gives me the PowerPoint. I will get it out to you just as quickly as I can. Thanks, guys. If you need anything, make sure you talk to your county agent, and we'll see you in next session.
Thanks.